welcome back. Now, since we covered carnivore and evolution last lecture, let's now discuss how we integrate characters in phylogenetic analyses using TNT. TNT, see Golubov et al., 2003, includes several new methods to facilitate phylogenetic analysis. Under an agreement between the Willy Hennig Society and the authors, TNT is now available as a free program. A version of TNT licensed for single-user academic use can be downloaded from the link below. The purpose of the module and present lecture is to provide a general overview of the program and some guidance for beginners. The forthcoming cladistic analysis includes 14 in-group taxa and 1 basal archosauriform, outgroup taxon Euparkeria. Unique sets of characters distinguish all in-group taxa. TNT is a fully interactive program. The Windows version has a sophisticated menu interface, which makes TNT the only major phylogeny program that can be menu-driven under Windows. The online help command includes a list of all the TNT commands and their options. Throughout, menu options are indicated as bold. To save space, only the most important and common options are indicated. Given a phylogeny, one can determine which character state is ancestral. The ancestral state of a character is the state found in the ancestor. Character states arising later are termed derived states. In practice, we cannot normally observe the common ancestor. Character states may be digits for morphological characters, question mark for missing data, or hyphen for gaps. To read in the data file, select File/Open Input File. Usually, you will name your data file with a TNT extension. Before analyzing the data, you should make provision for saving the output to a log file. This can be done by selecting File/Output/Open Output. Usually, you should give a log file the out extension and the same base name as the data file. A basic analysis consists of using multiple addition sequences, followed by branch swapping. To do this, select Analyze/Traditional Search with default options. Just click Search when the option dialog appears. This will perform 10 random addition sequences, followed by branch swapping, saving up to 10 trees per replication. In the case of small data sets, that is 15 to 30 taxa, exact solutions using branch and bound, which guarantee finding all trees optimal under current settings, can be produced within reasonable times with Analyze/Implicit Enumeration. Once calculated, trees may be viewed by selecting Tree Display. The tree can be saved as an extended metafile by pressing M while viewing the tree diagram. To save the trees for later reanalysis, create a save file by selecting File/TreeSave File/Open. Usually you will name your save file with a tree extension, that's TRE. If there are multiple trees, their consensus can be found by selecting Trees/Consensus. The synapomorphies common to several trees can be plotted on their consensus by selecting Optimize/Synapomorphies/Map Common. Selecting Trees/View switches to Tree Viewing Mode. Under Tree Viewing Mode, a left click on the node of a tree will select in red or deselect in green all the taxa descended from the node. In Tree Viewing Mode, trees may be locked or unlocked. This is controlled by the padlock toggle switch in the toolbar or by selecting Settings/Lock Trees. If the tree is locked, right-click on a node, shows a list of synapomorphies for the node. Character mapping and the diagnosis of the trees obtained are one of the main components of a cladistic analysis. TNT can either produce lists or sign apomorphies or character changes, or display those results on tree diagrams. With the menu options, optimize/sign apomorphies and optimize/characters, TNT allows an optimization of the multiple, most parsimonious trees individually, displaying on the consensus tree a summary of the changes that are common to all the trees used to produce the consensus. This is done with the common sign apomorphies or common changes option. The options for comparing trees and summarizing results are one of the most important aspects of TNT. The standard methods for consensus, strict, semi-strict, or combinable components, majority and frequency differences, are accessed with trees/consensus. There are quite a few types of consensus tree, but the more prominent are strict, evolutionary relationships that appear in all the trees. Semi-strict combine all possible solutions that are not contradicted, and majority rule, branching patterns that exist in a majority of the trees. If the relationship does not appear on all of the phylogenetic trees, it does not appear on the strict consensus tree. So long as no trees are contradicted by other trees, it can appear on a semi-strict consensus tree. The grouping only has to be present on the majority of the trees to be represented in the majority rule consensus tree. TNT implements several options that facilitate identifying the taxa responsible for the lack of resolution or responsible for the low group supports. For measuring group supports, TNT implements both Bremer supports and measures based on resampling, jackknifing, bootstrapping, or symmetric resampling. Bootstrapping is a useful means for assessing the reliability of your data. It refers to any metric that relies on random sampling with replacement. Felsenstein, 1985, introduced the bootstrapping approach to phylogenetic analysis. This is the most commonly used method for assessing sampling errors in estimated phylogenies. In this approach, the sites in the sequence alignment are resampled with replacement as many times as the sequence length, generating a bootstrap pseudo-sample that is of the same size as the original data set. Jackknifing differs from bootstrapping in that data points are not replaced prior to each resampling. For resampling, analyze/resampling, the user may define any search routines to analyze each resampled data set. After analyzing each resampled data set, TNT will automatically compute the strict consensus tree. Euparkeria is outside the Archosauria crown clade as it does not share certain synapomorphies. Its femur does not have an anterior medial tuber on the proximal end, for example. Since Gauthier 1986, Benton and Clark 1988, and Serino 1991 agree on its basal position in respect to other Triassic diapsids, Euparkeria serves as the outgroup in the forthcoming cladastic analysis. Data on this taxa derived from observation of illustration from Benton, 2014, page 156. The phylogenetic relationships of the Dinosauria have been debated for a long time, with several proposed hypotheses for these taxa. Euparkeria, Tawa, Herrerasaurus, Silosaurus, Plateosaurus, Heterodontosaurus, Coelophysis, Pietnascisaurus, Dilophosaurus, Pangoraptor, Allosaurus, Velociraptor, Archaeopteryx, Confucius ornis, Gallus and Struthio. Although the positions of these genera are still unresolved, the forthcoming cladistic analysis aims to provide the phylogenetic framework for characterizing the evolutionary history of dinosaurs. Empirically derived data on forelimb modularity is used to assess the impact of trait correlations on phylogenetic analysis of the Dinosauria, whilst paying particular attention to avialian relationships and the origin of aves. Data on Allosaurus derived from Madsen, 1976. Data on Archaeopteryx derived from Faktovsky and Y sample, 2012, page 228-229. Data on Coelophysis derived from Y sample et al., 2007, page 59. Data on Confucius ornis derived from Schiappi et al., 1999. Data on Dilophosaurus derived from Y sample et al., 2007, page 59. Data on Gallus derived from Burke and Fiducia, 1997. Data on Herrerasaurus derived from Fastovsky and Y sample, 2012, page 342. Data on Pangoraptor derived from Yeo et al., 2014. Data on Platysaurus derived from Y sample et al., 2007, page 245. Data on Silosaurus derived from Gierlinski et al., 2012. Data on Struthio derived from Burke and Fiducia, 1997. Data on Tower derived from Nesbitt et al., 2009. Data on Velociraptor derived from Norrell et al., 1999. In the wing of nearly all birds, the ulna is thicker than the radius, but in Archaeopteryx, the two bones are of equal size. In the wing of Archaeopteryx, there are 3 long digits with distinct metacarpals. In all other birds, the digits are modified, the metacarpals being commonly fused and the phalanges reduced in number. In the ostrich, as in nearly all Carinatae, the manus has 3 digits. The 3rd digit has 2 phalanges. In all other living birds, it has only 1 phalanx. Herrerasaurus was a genus of Saurischian dinosaur from the late Triassic period. This genus was one of the earliest dinosaurs from the fossil record. Paraves are a widespread group of theropod dinosaur that originated in the late Jurassic period. In addition to the extinct dromaeosaurids, troodontids, archaeornithids, and scansauropterids, the group also contains the avialans, among which are the over 10,000 species of living birds. Primitive members of Paraves are well known for the possession of an enlarged claw on the 2nd digit on the foot, which was held off the ground when walking in some species. Dromaeosauridae is a family of feathered theropod dinosaurs. They were generally small to medium-sized feathered carnivores that flourished in the Cretaceous period. The name Dromaeosauridae means running lizards. Anchisaurinidae is a family of Humaniraptorans, which could be the basalmost family of birds in the clade Aviali. Anchiornithids have been classified at varying positions in the Maniraptoran tree, with some scientists classifying them as a distinct family, a basal subfamily of Troodontidae, members of Archaeopteridae, or an assemblage of dinosaurs that are an evolutionary grade within Aviali or Paraves. Scansauropteridae is an extinct family of climbing, gliding Maniraptoran dinosaurs. Birds are dinosaurs because they share the derived characters of the dinosauria. Diagnostic characters that might be easily observed in the fossil record are used to deduce to whom birds are related. A diagnostic feature of living birds is the carpometacarpus. The scapular coracoid is the unit of the pectoral girdle that contains the coracoid and scapula. The coracoid itself is a beak-shaped bone that is commonly found in most vertebrates, with a few exceptions. The scapula is commonly known as the shoulder blade. The humerus is linked to the body via the scapula, and the clavicle is connected to the sternum via the scapula as well. A coracoid is a paired bone which is part of the shoulder assembly in all vertebrates except therian mammals. In therian mammals, a coracoid process is present as part of the scapula, but this is not homologous with the coracoid bone of most other animals. 33 binary and multistate characters were derived from observations or drawn from previous cladistic analyses. Binary characters avoid problems of hierarchical linkage, whereas multistate ones minimize character interdependency. All multistate characters were treated as non-additive. Unfortunately, this study contains missing entries in cases where data could not be found, as is often a problem in cladistic analyses. Using tree analysis, using new technology, an analysis of the data matrix was conducted to find the most parsimonious tree, incorporating all 33 four-limb characters. 16 fundamental cladograms resulted with 7 trees retained. Each cladogram has a length of 91 steps, a consistency index of 0.527, and a retention index of 0.511. Consistency index in cladistic analysis, a measure of homoplazy in a phylogenetic tree or cladogram. calculated as the number of steps, i.e. character state changes in the cladogram, divided by the smallest possible number of steps. The index therefore runs from 0 to 1. The retention index, Ri, is also a measure of the amount of homoplasy, but also measures how well synapomorphies explain the tree. The left cladogram shows Struthio and Gallus to be less derived than Confucius ornis, Archaeopteryx, Velociraptor, and Allosaurus. Therefore, four-limb characters are insufficient in themselves to provide a reliable cladistic analysis of the relationships between taxa. Gallus and Struthio share some four-limb characters with Taua and Silosaurus, hence their placement in a monophyletic clade. However, these characters appear to be plesiomorphic, as modern birds are shown to be polyphyletic with respect to them. The right cladogram, which integrates my cladistic analysis in the whole skeletal system, assesses the impact of trait correlations on phylogenetic analysis. This topology more closely resembles published works. Modern birds Struthio and Gallus form a monophyletic clade. Confucius ornis is paraphyletic with respect to Archaeopteryx. I hope you enjoyed that riveting lecture. We'll revisit that one later on when I teach you how to perform your own analyses. Thank you very much.